Hello everyone. Welcome to the VR&D webinar on VisualDOC version 8. We'll go through some of its new features and its capabilities. My name is Fani Aduri. I am a support engineer here at VR&D. I'll be hosting the webinar. Before I turn on the mic to our guest speaker, Dr. Lee Juan He, just a small introduction about VR&D and our products. VR&D, at VR&D, our mission is to provide the best software, best optimization software that will help designers achieve efficient products, and we try to do that with a team of experts, and we have a relentless pursuit of excellence. We have two product classes or product lines. One is the multidisciplinary optimization line, where the VisualDOC comes in. That's the flagship product for that line, and Dr. He will talk a little bit more about VisualDOC. On the structural side of things, we have another line on the structural side of things, and the flagship there is Genesis. We also have other interfaces of Genesis or GUIs related to Genesis, but Genesis is the flagship product there. Genesis, pretty much it covers everything in the linear regime as far as analysis is concerned. It is a fully integrated software tool, fully integrated analysis and optimization tool. As far as optimization is concerned, there is you can do topology optimization, which determines where you want to keep material and where you want to take out. You can do sizing, where any real property in your finite element model can be optimized. You can do shape optimization, where the location of the grids are moved to come up with an optimal shape for your structure. And on top of that, you can do other types of large-scale optimizations, like topometry, which is essentially element-by-element sizing, or topography, which in other words is called as beading optimization. And the last one is freeform, which is essentially grid-by-grid shape optimization. So the shape of the structure can be any shape. Apart from Genesis, we have a fast eigensolver that's called as SMS. It is available as a separate product and can be used along with DMAP with MSc Nastran, but it's also inbuilt into Genesis. So you can use, if you have Genesis or using Genesis, you can use the SMS fast eigensolver. And you typically gain more when you have larger problems and a large number of modes. ESL Dyna is our interface that extends the Genesis optimization to LS Dyna. It's based on the ESL method. ESL, in other words, is called as equivalent static loads, and it runs the Dyna solver. It can do all the large-scale optimization problems that Genesis can solve, but you're using the Dyna analysis or you're doing the optimization based on the Dyna analysis. We have a full integration of Genesis within the ANSYS environment, so you can use it as a backend tool and backend solver, and you can work within the ANSYS environment for ANSYS users, and do all the optimization that Genesis can do. Okay. On the multidisciplinary side of things, apart from VisualDOC, we have libraries for our optimizers, which are dot and big dot and discrete variable dot. Those are libraries that are available for third-party users or end users to wrap optimization along along with their code or software. With that, I would like to introduce our speaker, Dr. Lijuan He. Dr. He has been working with VR&D for about a year, more than a year. And she's working as an R&D engineer, and she is the primary developer for VisualDOC. If you have any questions regarding the presentation or any questions that you get during the webinar, please use the Q&A panel in the WebEx window, and we'll try to get to the questions at the end of the presentation. With that, I would like to ask Dr. He to share her desktop and present.
Thank you, Fanny. Good morning, everyone. Today, I will start by introduce one of the software products, VisualDOC, and then I will introduce the 3 new features in recent release in VisualDOC 8.0. VisualDOC is a general-purpose multidisciplinary design optimization software, which allows you to do several design tasks. For example, optimization, DOE, response surface, and etc. And it can be integrated with almost any analysis program, including Excel, MATLAB, Genesis, ANSYS, and so on. And is able to do multi-level, multi-discipline tasks at this same run. The most important for VisualDOC is our software is written by VR&D, and it's not a connection of public domain software. Here shows the history of VisualDOC. As I mentioned, VisualDOC is able to do several design tasks, including optimization, DOE, response surface approximation, probability analysis, and is able to integrate with many third-party CE software, and it has a direct interface to Excel, MATLAB, of software Genesis, and ANSYS Workbench. And it allows the analysis program to run remotely. And it has powerful simulation monitors to present the optimization solutions concurrently. The optimization process in VisualDOC includes 2 parts, optimization algorithm and the analysis program. The user imports the initial value for the design variable, and then the analysis program evaluates the outputs, and then optimization algorithm determines which will be the next design value of the design variable based on the output from the analysis program. And then this process continues until it is located the optimal solution. Here shows the analysis components in VisualDOC. It has the direct interface to MATLAB, Excel, and Genesis. And recently, we added the ANSYS Workbench component. The ANSYS component is an integration of executable and file input and output components that talks directly to ANSYS Workbench. In the previous version, the user can use the executable and file I/O, file input and output components to couple the ANSYS with the VisualDOC. But the user needs to set up the connection between the executable and the file input and output, and also needs to define how to extract data from the file input and output. And for the new version, the ANSYS components allows the whole process to do automatically. Here shows the data flow in the ANSYS component. Basically, VisualDOC writes the input data into the Workbench project file, and then the ANSYS Workbench executable evaluate the outputs and write the outputs into the Workbench project file, and then the VisualDOC reads the data, output data from the Workbench project file, and the process repeat until it converges. To perform optimization in VisualDOC using the ANSYS component, you first need to parameterize your model in the ANSYS Workbench. After you parameterize, all the parameters will be shown in the parameter list in Workbench table, as shown in this picture. And then you set up the VisualDOC, and all the parameters or data in this parameter list table will be extracted to two tables in VisualDOC ANSYS component. One is input data, and the other one is output data. And you can choose which parameters or output will be used in the optimization process by checking the use checkbox on the right of the table. After you set up, you can run the optimization, and after it's done, you can go to the ANSYS Workbench to check the optimized structure. Here is the interface for ANSYS component. In the VisualDOC 8.0, you will see ANSYS icon in the icon list. You can drag the icon into the canvas, similar with other icons. And then this is the workflow. This is the workflow when you use the ANSYS component to do the optimization. And you select the ANSYS in the model tree and then go to the component editor. It will display the property editor for the ANSYS component. Under the local analysis program definition panel, you can define the location of the ANSYS Workbench executable. And then you go to the project file definition and to define the location of the ANSYS Workbench project file. After that, you click the Load Data button, and then it will automatically extract all the data into these two tables, input data table and output data table. The first example, I will show how to couple the VisualDOC with ANSYS Workbench Mechanical. This is the parallel lifter. It will be located on these two parallel arms. And the objective for this problem is to minimize the total mass of the structure under the constraint of maximal stress and displacement. And the design variable for this problem is the thickness of all the components except the fixation support on the top. So here is how the workflow looks like for this problem. And you click the you select the ANSYS component and the model tree and click the component editor. It will show the property editor. Here for this problem, all the input parameters is extracted here and output in the output data table. And there are some toolbars at the end of in the bottom of the table to help you manipulate the data in the table. For this problem, we will use all the parameters for the optimization. So we select all the parameters in the table. After you set up the ANSYS component, you go to the data linker panel to link the data. For this problem, to maintain the symmetry of the structure, some of the data will be connected to in the optimization component will be connected to two parameters in ANSYS component. After you link data, you set up the optimization component. For this problem, we use gradient-based optimization. It takes 12 iterations to converge, and the total mass is reduced by 28.5%. The second example will show how to couple VisualDOC with ANSYS Workbench Fluent. This is outbound, and the code flow is injected into the pipe through the big inlet, and the hot flow is injected into the pipe through the small inlet. The objective is to minimize the average outlet temperature at the outlet. And the design variable is the radians of the torus and the angle theta and beta. These are unconstrained optimization problems. So here shows the setup in VisualDOC. And it took 3 iterations to converge. And the temperature drops from the initial temperature 299.2 to optimal 298.8. So in VisualDOC 8.0, we add a new response surface model, kriging, into VisualDOC. Mathematically, the predictor of the kriging model interpolates the data using 2 models, interpolation model or trend model, which represent the trend or the global mean of the prediction model, and the stochastic model, which represent the local deviation from the trend to the point, and is assumed to be a Gaussian process with 0 mean and covariance calculated as sigma square multiply the coordination matrix. As I said, the kriging model is added to our DOE component. When you go to the DOE property editor, under the DOE model, you will see the quick-in model. And after you click the quick-in model, the quick-in model setup panel will be displayed. And then you can use it to set up your quick-in model. In order to use the quick-in model, first you should choose the type of regression model. There are 5 types of regression model in VisualDOC: constant, linear, mixed linear, and interactions, mixed linear and pure quadratic, and full quadratic. The equation on the left gives examples of the mathematical forms for the models in 2 dimensions, but it can be extended to higher dimensions if you want. After you choose the regression model, next you should choose the coordination model. Coordination indicates the extent to which 2 variables have a linear relationship with each other. Normally, it's a function of a distance between these 2 points. And we provide 5 coordination models: absolute exponential, Gaussian, generalized exponential, and linear and cubic. So next is to define the regression weights. VisualDOC provides 2 options to define the regression weights. The default one is to fit the regression weights by generalized least square. You can also choose to provide the regression weights if you have the information of the regression weights. Then by clicking the user-defined regression weights checkbox, and then the text field of the regression weights will be active, and you can enter the default value for beta. If you want to provide different value for different value for regression weights for different response, you can click the create and edit array for beta. Then it will initiate a table to set up the regression weights for different response. The first row is the default value, and you only need to enter the beta value, which is different from the default value. The blank entries indicates the beta value is equal to the default value. And next, you set up the coordination parameter theta. The coordination parameter can be obtained by maximal likelihood estimation. It's an optimization problem, so the theta value you entered in the coordination parameter theta text field is the initial value for the optimization of theta. And you should also choose the define the lower bound and upper bound of theta. And also, if you know the coordination parameters, you can provide the information of the parameters by checking do not optimize the coordination parameter checkbox. Then in this case, the algorithm will skip the maximal likelihood estimation and just use the theta value you provide to predict the value using the quick model. Same as the regression weight beta. If you want to define different, theta values for different design variables, you can click the create and edit array for theta. It will initiate a table for you to define your data value. After you set up all the parameters, you can start run the DOE component. After it's done, you can go to the post-processing to visualize the model. Similar as other models, similar as other DOE models. You can visualize it in 2D and 3D view. And the detailed information of the model is printed in the summary report. So when you go to the summary report, you will see the following information printed for the Kriging model. You can predict the Kriging. You can predict the output using the Kriging outside the VisualDOC by using the equations listed on the left. And then the first table contains the information of coordination parameter theta corresponding to different design variables, as well as the mean and the standard deviation of the design points. This information is necessary because VisualDOC fits the Kriging model using the scaled sample points. So when you use the Kriging model to predict, you first need to scale your input value, and then predict the output, and then scale the output back using the mean and the standard deviation of the response printed in the second table. And then the third table includes the information of the regression matrix data. And the third one is print the gamma matrix, which includes the coordination information in order to predict. And the last one is the scaled design matrix, which will be used to calculate the Rx matrix. Here I will give an example to show how to do optimization with the Kriging model. This is a cantilever beam, and the objective is to minimize the volume of the beam under constraint of displacement and maximum stress. And then design variable is the width and height at each of the cross-section. This is the workflow for this problem. And for this problem, I use the default setting for the Kriging model. Here shows the result. It's very close to the ones obtained from the optimization without using meta model, without using DOE. At the end, I will show why the VisualDOC is your best choice. VisualDOC has a powerful optimizer, including DOT and Big DOT, which are developed by VR&D and are continuously enhanced. And VisualDOC is user-friendly, including intuitive process integration and real-time design monitors, and etc. And we have over 30 sampling design methods, and it has a direct interface with our product Genesis. So thank you for attending. Any questions?
Thanks, Lijuan, for the presentation. At this point, I would like to mention that if you have any questions, please use the Q&A panel and post your questions there. We are going to go through those questions. While we are waiting for questions, I just want to mention a couple of things. We do offer fee evaluations for the software, for any of our softwares, by the way. And if you would like to evaluate the software, visit our website at www.vrand.com, and there is a link for requesting an evaluation. We have done several webinars in the past. All the recordings are available on the WebEx site, www.vrand.webex.com. As I mentioned earlier, any questions, please use the Q&A panel in the WebEx window. Our next webinar is in about a month's time. It is on July 13th, and we will be talking about the interface or the integration of Genesis within the ANSYS environment, specifically with ANSYS Mechanical. We are going to talk about some of the new features that we have added there. It will be presented by Dr. Hong Dong. She is the primary developer for that interface, and she's going to talk on July 13th at 11 a.m. Eastern Time. We will send out an email announcement for the same in sometime next week. Also, I do have a recording of the webinar itself, and I will provide that recording in about a week's time to all your emails. Okay. All right. Moving to questions. One question, Lijuan, is can the kriging be used inside of an RSA component? As of now, do you allow the kriging to be used in an RSA component or not?
Currently, yeah. Currently, it's not allowed. We only add the kriging model to our DOE component, but in the future, we will add the kriging model to our response surface approximation optimization component.
All right. Okay.